So in this video, we're just going to go over how to graph a parametric equation by hand. So for this example, we have is two different sets of parametric equations. Here I have x equals t squared minus 1 and y equal t. So here's one set of parametric equations. And we want to graph the plane curve generated by these parametric equations over the interval from -1 to 4. So we're saying t is an element of the closed interval from -1 to 4. And you would do this simply by making a table of values. So we know what y is with respect to t, and we know what x is with respect to t. So we would simply pick numbers on the interval from -1 to 4 and plug them in for t, both for the function y and the function x. So if we do that for y, because y is equal to t, if we come over here and let's graph this guy down using this table, if y is equal to t, for the y values we simply get the t values. So in your table of values, if t is equal to -1, then y is equal to -1. If t is equal to 0, y is equal to 0, and so forth. So the row for y, the outputs for y, would be the same as the inputs for t, because y and t are the same. And to generate the row with the x values, we would just simply plug in values for t over the interval from -1 to 4. So plug -1 in, we get -1 squared is 1, minus 1 is 0. Plug in 0 for t, you get 0 squared minus 1 is -1. 1 squared minus 1 is 0. 2 squared is 4 minus 1 is 3. 3 squared is 9 minus 1 is 8. And 4 squared is 16 minus 1 is 15. And then once you have generated your values for x and your values for y by picking values for t that live on the interval you're interested in graphing over, you simply construct the ordered pairs. This would be the ordered pair 0, -1, which I've graphed right here already. This is the ordered pair -1, 0, which I've graphed right here. This is the ordered pair 0, 1, the ordered pair 3, 2, the ordered pair 8, 3, and the ordered pair 15 and 4. And then once you graphed your ordered pairs, you would do the same thing that you've always done after you've created a table of values. You try to as neatly as you can connect the dots smoothly. And in fact, this particular set of parametric equations was a sideways opening parabola that I parametrized. So you go in and you try to draw it as smoothly as you can. I'm not going to go past it and put arrows, because I was only asking to describe the plane curve over a particular interval or domain. So we end it at the points. And then the other thing that you have to recognize is that when we have parameterized curves, they have a direction to the parameterization, and you need to include the direction information in your graph. So as t gets bigger, going from -1 to 4, we start at this point and we are moving our way around the curve kind of in a clockwise direction. So I want to add some arrows to the curve indicating the direction in which the graph is sweeping out through the xy plane. So you have to pay attention not only to the ordered pairs, but the ordering of t. T is in ascending order. So we're moving from ordered pair to ordered pair in the parameterization. So there's a direction to this motion. To graph this set of parametric equations, we would just do the same thing. We would create a table of values. So we look at the interval over which we are interested in graphing. So t is an element of the interval from -2 to 8. And then we would select values for t along that interval. So I've chosen -2, 0, 2, 4, 6, and 8. And all I've done then is gone through and plugged in these numbers for the y and the x equations. So for example, y equals t over 2. So I did -2 going in for t. -2 divided by 2 is -1. 0 goes in for t. 0 divided by 2 is 0. Then I did 2 in, 2 over 2 is 1, 4 goes in for t, 4 over 2 is 2, 8 goes in for t, 8 over 2 is 8 over 2 is 4, 6 over the 2 is the 3. So I generate the y outputs that go with the t inputs I have chosen in the interval of interest I have. And then we do the same thing to get the x values. We plug the pieces in. So we plug in the negative 2 goes in here. Negative 2 squared is 4. 4 over 4 is 1. 1 minus 1 is 0. 0 goes in here. 0 squared over 4 is 0 minus 1 is negative 1. 2 squared is 4 over 4 is 1 minus 1 is 0. 4 squared is 16 over 4 is 4 minus 1 is 3. 6 squared is 36 over 4 is going to be our 8. And then 8 squared is going to be 64 and 6 squared is 36 over 4 is 9, and 9 minus 1 is our 8. And then 8 squared is 64 over 4 is 16, and 16 minus the 1 is the 15. And if you look at the two tables carefully, you'll see that the outputs generated for both x and y are identical. And as t moves from small to big, we're moving from ordered pair to ordered pair. So it turns out that the graph for this table is exactly the same as the graph for this table. So there would be nothing new to construct in this case. And the idea here is that these two parameterizations, both of them were for the same sideways opening parabola. I parameterized the sideways opening parabola x equals y squared minus 1. And what I did is I parameterized it two different ways. So as long as I pick the intervals I'm interested in carefully, I can get them to match up exactly. The idea behind having this as an example is to bring to the forefront, or to your understanding, that parameterizations of rectangular equations are not unique. In fact, for any given rectangular equation that exists, there are infinitely many ways to parameterize it. So parameterization is not unique, and we'll look in subsequent videos on, we'll look at how you parameterize an equation.